So the aim today is to talk about nuclear fusion. Well, mostly to skirt the issue of nuclear fusion, just to show you guys what nuclear fusion has in common with other energy-producing processes, how we get energy, how we use energy, and why nuclear fusion is suited from a resources point of view to use in space in terms of both travel and colonization. So let's get right into the first topic right here. So one of the questions we have to answer when we know we want energy, right? Because energy is the capacity to do work. So we have to answer how we get energy. First, I'm going to provide a kind of rough math-free definition of energy. So energy is, like I said, the ability to do work. Everything you want to do requires energy. And some of the processes you can find in nature output energy naturally. And some of the materials that you can find in nature have energy stored in them, in the sense that you can perform some operation on them, and they'll collapse from a high energy state to a low energy state and emit some energy in the process. And this is not just, you can tell from my vocabulary, I'm from quantum physics, but this is not necessarily quantum. If you find a ton of coal in the ground, combined with oxygen, it emits energy. Right? And that's energy you can use if it's heat or energy in the form of kinetic energy in fluid. You can tap that and really produce electricity, which can be piped around to everybody else. Make everyone happy and provide enough cold beer and hot showers to run civilization. So two main definitions. What I need to talk about is potential energy, which is the energy that marbles have at the top of this structure, and kinetic energy, like I said earlier, the energy it seems moving. Right? So that energy, which is inherently linked to motion, which is increased as the balls roll down the structure, and potential energy, of course, is decreased until they get out to the end here. They roll until friction stops them. Right, so how can we find some of this energy that is stored ubiquitously around us in nature? The general principle is what I like to call the mousetrap principle. You have to find where there's a big separation in energy, right, like a mousetrap that's been pulled back, so there's a lot of energy bound up in that spring, and a way to release that energy. So if you have two masses that attract each other, suppose there's a cloud on the Earth, right, they attract each other gravitationally, and eventually the Earth will, or precipitation will trigger this cloud to become a bunch of rain droplets and fall down, and you can capture that energy in principle when you have a water wheel, right, like the ancient Romans used to use here. Right, this is just a diagram detailing the energy from the sun, drives this process, essentially providing kinetic energy for this fluid that runs around in a cycle that we can tap into at any point. Another one of the ways you can take advantage of this gravitational mechanical energy system is to use a windmill. Basically, the sun heats. The sun, because the Earth is not a homogeneous sphere, the sun heats water differently than it does Earth. Temperature difference drives a wind current that you can tap into the windmill, which is essentially similar to the water wheel, the only difference being density, the density of the fluid that you're tapping into. The way we get most of our energy right now, however, is through chemical means. So you can dig up coal, oil, propane, or you can use biologically produced chemicals, right? Wood, cellulose, methane. Combined with oxygen, which is ubiquitous around us, it forms 20% of our atmosphere, in order to release heat, which you then use to generate electricity as per the common formula. What I've shown here is, so this gives you a good idea of the two states that are involved. So you have methane and oxygen. Right? This is a very high energy state. These hydrogen atoms don't want to stick to this carbon. They want to be drawn to the very electronegative oxygen. When they react, energy is released because this configuration has a lower energy for it's more tightly bound than this configuration. Right? And all this will be roughly quantified in this app. Right, so to recap, how do we get useful energy? We have to identify a pair of forces that counteract each other. Just like a mousetrap, you have a force of the hook and a force of the spring, and then you have to find a way to trigger the release of the energy stored in one of those forces. Or you can find somewhere where that release has already been triggered or is happening continuously, right? Like in a moving fluid, global currents, the tides, wind, or solar energy, which is in fact just the example of where this release of energy has already been triggered at the nuclear level, and we can collect the runoff. Intuitively speaking, this process is much simpler and provides for much less waste because you don't have to go and get into any hard-to-reach area in order to mine the chemicals, or you don't have to use a lot of land to grow the wood or whatever that you want to burn. But the energy densities that you can get and the amount of energy you can get for $1 as a consequence is usually much greater when you use this method. Now to get into the second section of the talk, we're going to talk about the components of an atom so that we can explain how a nucleus can be used to store and release energy. So an atom consists of two parts. You have the nucleus, which exists at the center, right here, which is about a femtometer across. It's 10 to the minus 15 meters, so a millionth of a nanometer. And then this one is, the electron cloud surrounding it is much larger. This diagram's not to scale, don't worry. It's an angstrom, which is gigantic in comparison. It's a tenth of a nanometer. Right. And you can see these two things, because the nucleus is positively charged, the electron cloud is negatively charged. These two things, usually act in some sort of balance or stasis to form a stable atom. Right, so I'll just go over the invisible nucleus. So we'll be ignoring the electron cloud from this point on and concentrating solely on nuclear physics. So here's a crude drawing of the nucleus here. You can picture, and I'm drawing these as fuzzy because, according to a qualitative description of quantum mechanics, you can't pin down the position of any one of these things with absolute certainty. They're kind of like little fuzzy blobs of matter. So here we have protons, which have a positive charge, and neutrons, which have no charge. We know from basic, electromechanics, or Bill Nye, or shuffling your feet along a carpet and then trying to touch a balloon, that opposite charges attract, like charges repel. So if we have a bunch of like charges, it's unintuitive using the forces that we can see in our regular lives, how we would keep these nuclei together. There's a semi-famous evangelical Christian comic manufacturer called Jack Chick. He makes these little things called Chick tracts. You've probably seen one or two of them. And in one of them, he claims Jesus is holding the nucleus together. I thought that was a very elegant description, but it's actually something called the strong nuclear force, which I imagine you could just as easily name Jesus. But we call it the strong nuclear force because it acts on these femtometer length scales, right? It dies off very quickly outside of those length scales, which is why you don't see it, attracting chairs to walls or something like that, because these things contain nuclei. Right, and it's strong within that short distance. And obviously it's a force, so we gave it a very broad description. It's kind of like dark matter. We don't understand what it is, but we can see a couple of its qualities. So we call it the strong nuclear force. It's just a placeholder, it doesn't imply to understand it. But wherever you have the strong nuclear force and the electromagnetic force, or the electric force in this case, because we're talking about charges, countervailing each other, right? We have those two counteracting forces. And if we can trigger a release of one of those forces, we can emit some energy in the process.